Hi everyone, I hope you all are safe and doing well. So let us start the next video in this concept video series. So in the first two videos, we mainly focused on segment tree. Now in the next two videos, we will be mostly focusing on Fenwick trees. So you may know Fenwick trees by its other name, that is binary index trees. So these two videos, so the first video will mainly be the introduction of Fenwick trees, and the next video we will see how to implement Fenwick trees. So let's go. So why do we use Fenwick tree? So point number one, it is much easier to implement than the segment tree. So we did see the segment tree implementation, right? And not gonna lie, but it was pretty hard to implement it. So see, once we break down all the steps, it seems easy, but the implementation itself, it's long and it's hard. So it is pretty easier to implement than the segment tree. So point number two, problems where we have to increment any array element and calculate value of some function between a range 1 to x are its best use cases. So now imagine you have such a problem that you are given an array and you have been told to do two operations. So the first operation is that you have to update or increment any array element. Okay, so say you have an array element a of I and you have to increment it by v. So the new value of it should be ai plus v. Now this is the first operation, and the second operation is that you have to calculate the value of some function between the range 1 to x, where x is some index. Now there is a limitation on this function that it should be a reversible function. Only then you can use a Fenwick tree. Okay, so we have to calculate the value of some function between the range 1 to x. So in these two operations, the update and the query operation, so calculation of the value of some function, so these two can be implemented by a Fenwick tree. Now what is exactly the difference? In a Fenwick tree, you get the answer from 1 to x and not from L to R, right? So you cannot specify a two bounded range. You have to just specify the right endpoint and we get the answer from 1 to x. Now it is obvious that you can find the answer however you want, like 1 to x, and so if you have L comma R, you can find the answer from 1 to R and 1 to L, and then do whatever you want. And the third point is that it can be implemented iteratively with the same time complexity as of segment tree. And you know the time complexity, it is O of log n for both operations. So we have generally seen now why Fenwick tree, in what cases will we use Fenwick tree. So now let us directly proceed to how Fenwick tree works. So now let us see how we will be constructing a Fenwick tree, or as we can also say, a binary index tree. So first let us see that for what kind of question we will use it. So let us say we have been given two operations. So the number one operation is to update say value of index I by v. So this update operation is generally that we will increment the value of a of I by v. So this is the update operation. And the second operation is that we have to sum from a range 1 to x. So here we will just be given an integer x, and we have to return the sum of say a1 plus a2 plus up to ax. So now also note that in this tutorial I will be mainly using one based indexing, since it's easier for explanation and also implementation, and you will soon see why. So basically this is the kind of operations that we have been given, and now let us try to apply binary index tree to solve it. So you already know that if you use brute force, then the complexities of the above operations. So for this operation, if you use brute force, it will be O1, because you can directly update that respective array element. And if you use obviously brute force, then for sum you will have to do it on, because every time an element gets updated, you will have to update the prefix sum every time, and that will cost on every time. So this is generally not desirable. That is why we use Fenwick tree over here to give us log n time for both these operations. So now let us see how to apply Fenwick tree to solve this kind of problem. Now, over the course of this implementation or this introduction, you will see that it is called Fenwick tree just because it can be represented like a tree. But in our introduction, we will see that how we can easily represent it as an array. So no need to visualize it as a tree. So now, first thing that we are going to do is for Fenwick tree, that for each index associated with the array. So these are the index. For each index, we are going to store the sum of some range on that index. So here we have the bit array. So in the bit array, we will see what index sum we are going to store. So yeah, so I forgot to tell you that we are going to be implementing the sum Fenwick tree for the sum type of queries. So here the type of queries will be A1 plus A2 up to AX. Okay. Now let us directly start. So before starting, we will see that for any index I, what type of what type of sum ranges that we are going to store over here. So for any index I, we will be storing I minus 2 to the power R plus 1 to I. So this is the range that this is the sum in the range that we are going to store. So what is R over here? So R is the LSB of I. So what is LSB? As you know, LSB is the least significant bit. Now let us see how we will be calculating LSB. So if we see 6, so the LSB of 6 is, so the binary representation of 6 is 110, and the LSB of 6 is this. So this is at position 1. So if this is position 0, this is position 1. So the LSB of 6 is at position 1. Now let us see how we will implement this. So we start from, so here I have I minus 2R plus 1 to I. So now let us start from 1. So the binary representation of 1 is 1. So R will be 0 over here. So for 1, the value of this will be 1 minus 2 raised to 0, which is 1, plus 1. So it is basically 1 to 1. So here, at index 1, we will be just storing the element itself. So 1 over here. Now for 2, let us see the binary representation is 1, 0. So R is equal to 1 over here. So 2 minus 2 raised to 1, which is again 2, plus 1. 2, 2. So here if you see, it is 1 to 2. So here we are going to store the sum of elements 1 comma 2. So A1 plus A2 will be stored at bit of 2. Okay. So similarly for 3, we can see it is 1 comma 1. Therefore R is equal to 0. So 3 minus 2 raised to 0, which is again 1, plus 1. So basically only 3. For 4, if you check, it will be 1 comma 4. For 5, again it will be 5 itself, because the LSB is again R is equal to 0. For 6, it will be 5 comma 6. Just a minute. For 7, it will again be the element 7 itself. For 8, it will be the whole range from 1 to 8, since here the binary representation of 8 is this. So R is equal to 3. So this, putting into this formula, it will be 8 minus 2 raised to 3 plus 1. So it will basically be from 1 to 8. For 9, again it will be just 9, since LSB is again 0 over here. And for 10, it will be 9 comma 10. So these are the values that we are going to be storing in the bit array. So basically here it is 1, here it is A1 plus A2, here it is just A3. Oh, sorry, here it is A1, here it is A1 plus A2, here it is A3, here it is A1 plus A2 plus A3 plus A4, and so on for each of these elements. So I hope you've understood that how we are going to be constructing our bit array. So this, so we have constructed our bit array. Now the next thing that we are going to do is we are going to see how we are going to calculate the sum of like any range from this bit array. So for the range sum, we know that we are going to be given an input x, and we have to give output of the sum from index 1 comma x. So let us see. Let us see now how we are going to find the range sum query given any integer x as input. So let us say we have x as input, and let us say that x is equal to, say, 6. Now note that this is a diagrammatic representation of how the ranges are. So here you can exactly see. So this is exactly what we calculated with the earlier formula, that I minus 2 raised to r plus 1 to I will be the range for each I, and R will be the LSB over here. So for x is equal to 6, let us see what is the binary representation of 6. So 6 is basically 110. So now our procedure to calculate the sum, it will be as follows. So the first thing, it will be that taking 6. So basically for sum of x, it will be, first thing that we'll do is it is equal to, so let us have our result is equal to 0. So this will be our answer. Okay, so first thing that will be do that we will do is result plus equal to bit of x. So now basically we are going to add the range from bit of 6. So what is bit of 6? It is the sum of a5 plus a6. So what more that we need to add over here? We need to add the sum of these four elements, right? So the next thing that we are going to do is we are going to remove the rightmost set bit. Okay, so which is the rightmost set bit over here? This one, right? So after removing this, this will become 100. Okay, so now what we are going to do is we are going to add the sum of this. So basically now removed right set bit, and again we are going to repeat the same thing, that we are going to do res plus equal to bit of x, but now x is different. X is not 6. What is x over here? X is equal to 4. So for 4 we have a1 plus a2 plus a3 plus a4, and it is exactly what we wanted. So now if you check, res has our sum that is required, which is a1 plus a2 up to a6, right? So basically this is the algorithm for giving us the answer. Now let us see one more example for the same, so that it will help to clear things. So let us take say x is equal to 9. So let us see what is the binary representation of 9. So 9 can be written as 1001. So let us see what we will do. So we will have a res is equal to 0. So the first thing that we are going to add in res, so res plus equal to bit of 9, right? So what is bit of 9? Bit of 9 is the same element 9, as you can see over here. Okay, so with 9 we get the same element. Now we are going to remove the rightmost set bit. So this will become 1000. Okay, now the next thing that we are going to do is we are going to continue this process. So what will it become? Res plus equal to bit of, what is this number? It is equal to 8. So bit of 8. Now note that this process has to be continued until this number becomes 0. So now after you remove the rightmost set bit over here, so what is the rightmost set bit? So there is only one bit. So after you remove this, it will become 0. So res plus is equal to bit of 9 and res plus equal to bit of 8. So what is bit of 8? It consists of sum of numbers between 1 comma 8. So and as we know that bit of 9 is just 9 itself, therefore we got our answer that the range sum of 1 to x, we got it. It is again a1 plus a2 up to a of 9. So this was achieved by just adding these two indices of the bit. So this was the formula. Now let us just try to write a pseudo code for this. So the first thing that we have x as input. So what we will do with x, we will initialize res is equal to 0, and then we will add res plus equal to So sorry, while x not equal to 0, then we will do res plus is equal to bit of x. Okay. Now what we will do, remove rightmost set bit in x. Okay, and then this will continue. So, and return res. So this is basically the pseudocode for finding sum between 1 to x. So now in the next video we will see how to implement it. So its implementation is really easy, and if you understood this code you will be able to do it yourself. So let me know if you have any doubt in this video, and see you next time.